Sir. So this is a demonstration of our project, which was developed by myself. I am Karthikeyan Bairu, and including my friends Sandeep and Avinash. So our project is interprocess IPC using shared memory in QNX Neutrino RTOS. It is basically implementing shared memory concept in QNX. So introduction to interprocess communication. So IPC mechanisms is a backbone in modern real-time operating systems. It's actually exchanging of data between different processes. So it uh, essentially includes three main features that are data exchange. So IPC interprocess communication enables processes to share information, coordinate tasks, and work together to accomplish complex system objectives in distributed architectures. So we'll discuss this about in the next slide in detail, and it should be performance critical as performance. So basically, real-time operating system uh, should meet the should meet the deadlines before, because it is more critical and it is used in hard real-time systems. So it should be performance critical, and it also should consist of safe communication. It is nothing but proper synchronization, which will ensure data integrity and prevent race conditions. So for synchronization, we use Mutex and Semaphores, etc., like those mechanisms. So our project demonstrates fast data exchange between processes using shared memory by using QNX Momentex IDE, which will be explained by my friend Sandeep afterwards. So our project objectives include developing a shared memory communication model, so which will be developed in QNX Momentex IDE. It's actually interprocess data exchange that maximizes performance while maintaining data integrity and process isolation, and master synchronization primitives. So I have already mentioned about mutex and semaphores, which are different synchronization primitives to achieve synchronization in shared memory, which work in QNX Neutrino, and also implement producer consumer architecture. So we can also refer it as a client and server architecture. So it's actually producer consumer pattern that demonstrate proper synchronization, buffer management, and error handling in a multi-process environment. And a bit QNX Momentex IDE, when the project has been implemented in the QNX Momentex integrated development environment. And for our project, there are some background concepts which are shared memory, semaphores, and QNX neutrino RTOS, like we have discussed in the previous slide. So these mechanisms range from message passing and pipes to shared memory sockets, each with distinct performance characteristics and use cases. So shared memory, we already discussed. So it's actually the fastest IPC mechanism because it eliminates kernel mediated data copying, so that physical memory region can be accessed by multiple processors. So that's why it got the name shared memory. So in this we use different functions. The main functions are SHM open. So shared memory open, it creates or opens a shared memory object, and mmap, which is a memory mapping, maps shared memory into process address space, and ftruncate, which actually sets the size of shared memory region. And semaphores, like it is achieved for the synchronization. It is used for synchronization. So synchronization can be achieved by semaphores. It's actually they prevent race conditions and ensure data consistency by controlling when processes can access shared resources. And QNX Neutrino RTOS, real-time operating system. QNX Neutrino is microkernel based architecture. So and also it is provide full POSIX API support. Because of its microkernel architecture, it's highly reliable and it's highly scalable, and it can be quite helpful in real-time applications. Uh, and my friend Sandeep gonna continue uh, further slides. Thank you.
Self, Sandeep, as my friend Karthikeyan said about the theoretical way of project. So I want to implement in a practical way. I want to showcase the practical output of an our project. So basically, he said that our project consists of three files: producer, consumer, and shared memory. Shared memories act as a common between producer and consumer. So producer will write a message in the shared memory. The shared memory is accessed to the consumer also. So the consumer will take the messages from the shared memory. It is an IPC communication. The shared memory, we choose the shared memory because it is the fastest way to communicate between the two processors. We are implemented a basic project to showcase the communication between two processors. The two processors are like producer and consumer. So let's discuss how we have implemented the project. So the tools and technologies we have used in our project is like first one is QNX Neutrino RTOS. So we use the QNX since QNX is an microkernel architecture and it is a real-time operating system we used in the embedded it will use in the embedded system. So it supports the POSIX library API application program interface, and inbuilt functions are many APIs and functions are available in the POSIX. So we have choose the QNX Neutrino RTOS. And coming to the IDE, we have used the QNX Momentix where we can write the code. IDE is nothing but an like similar to a notepad where we can write the code. So for coding, we have choose the C programming language. Since C program is directly interactive with the hardware part, so we choose the C program. Most of the operating system uses the C program language. So coming to the core APIs and functions, I will explain these functions in during the program execution, like shared memory open, mmap, shared open. This shared memory open is used to create a shared memory object. Coming to the mmap, we will the address of the shared memory is located to an processor. It is similar to a connecting a processor to a shared memory to make interact between the shared memory and processor. We use the mmap. And coming to the pthread mutex, we use the mutex. Mutex is an synchronization technique where we can lock and unlock the critical part of a code. And if truncate is to set the size of a shared memory. And detail I will explain these variables in during execution of program. Let's move next. So the implementation overview is nothing but just we have created a shared memory first. The shared memory is created by a producer. We use the for creation we use the shared open, and to set the shared memory we have truncate. And coming to map the processor to a shared memory, we use the function inbuilt function called mmap. And coming to the for the synchronization purpose, we use the mutex and semaphore. As we know that semaphore is used for the locking and unlocking, and we use the semaphore. Semaphore is an variable used in the multiple process. Semaphore is used since to wait the process until the message filled or are unempty. The semaphore variables we have used like semfull and semempty. Semfull indicate that the buffer is full or not. Coming to the semempty, semempty indicate that buffer memory is empty or not. So for those we use the semfull and semempty semaphores. Coming to the implementation of producer consumer logic, we executed both parallelly and to check the messages are executing in the buffer and the consumer is consuming the message. So proper synchronization, we use both Mutex and Semaphore. And coming to the code structure, we have created a two .c files for writing the code, one header file because the header file consists of a declaration of variable declaration function. So we declared a struct keyword. This is the struct keyword is a shared memory structure where the producer and consumer both will utilize. So we have used the shared dot header file to use both producer and consumer. Coming to the execution of an QNX Momentix ID, let's move to the ID. First, what we have to do? First, we have to create a separate project. We have created that. Then we have to build a project, execute, and mount. Let's look at the project. See, this is our project, share.h. This is producer.h and consumer.h. In share.h, we have declared an structure called SMHM control. This structure is used by both producer and consumer. In the structure, we have declared a uns unsigned integer 32-bit magic version mutex variable head tail. These we have used head and tail to locate the messages where we are inserting. The head pointer is used by the consumer and the tail pointer is used by the producer. When the producer will write a message in the buffer, the tail pointer will increase. When consumer consume the me- message, the head pointer will decrease in such a way that we use head and tail. And we declared a buffer slots like buffer slot and slot size. We have created a slots of buffer 8 and each slot consists of a 256 byte. So total 8 slots are available. So coming to the producer.c file, we included some header files. And coming to C, here we are creating a shared memory. This is a shared memory. Open. Open means it will create a shared memory. Shared memory name. The shared memory should consist a name. The name was declared here. Shared memory, my shared memory IPC. And full name was my shared full name. Empty name. Like this declaration are declared in .h file. It is used by the .c producer files because we have included the header file here. So o.create is open creation, o.rw is open read or write. So we are creating a shared memory, or else we can read or write using the shared memory. This is an privilege number which has some accessible 666 accessible, and after opening, we are setting the size of a shared memory f truncate, setting the size some uh, SHM size. The size was we have declared in .h file. SHM size. This was the size. The 8 slot 256 byte each slot consists of. So we have created buffers. We have set the size of a buffer, and we have to map the buffer to an processor. So we use the mmap to set the mapping the buffer to a processor. So we use a control pointer. This is the pointer where we can access the buffer using this pointer. So first we access this pointer. From this pointer, we will produce the messages into the buffer. So coming to the, we have initialized the mutex. Since we are using the mutex, I already mentioned that when the processor is using a buffer, the the mutex will lock the processor. It doesn't allow the another process to enter the buffer. So in this way, so we have used the mutex. So we have initialized and created an attribute, initialize a mutex, and we destroy. To create an mutex, we use an attribute. From attribute, we initialize mutex and destroy that attribute. So these are the two variables we use, semfull and semempty, for checking that the buffer is full or not or empty or not. So coming to the producer problem, we have a slot size, message, sem weight and sem full to check the whether the buffer is empty or not. After same wait, we will go to the mutex, lock the buffer, and later after locking the buffer, it will put the messages in the buffer, and later after putting the message, after completion of processor, it will unlock the buffer. And later we go to the consumer problem. The consumer will open the shared memory which was created by the producer, and it will create, and it will take the variables like same full and same empty to check whether the full or empty. It will wait until the messages are filled in the buffer. After filling notification, it will lock the buffer, and it will complete the job. It will consume the messages from the buffer, and later consuming the message, it will unlock the buffer. After unlocking the buffer, it will complete job, and it will give a notification to the producer. Let's implement our project. To implement, we have to build the target. So we can by clicking double click, we can build the target of consumer, and later we can build a producer. So we have to run the binary files of producer first, because the shared memory was creating by producer. So we have to run the producer first, then later we have to run the consumer. So we can see the output that producer had started. So it's writing messages into the buffer. So we can't see the messages of the writing, because the buffer, when it is creating the message, the consumer is consuming the message in within a fraction of seconds, so we can't able to see those messages. We can observe that consumer received message 1 2, so it's writing the messages into the buffer, but consumer is taking those message within a fraction of seconds, so we can't able to see the producer messages. This is our project, final project, and later my friend Abhinash will explain about the future enhancement, and what are the advantages of this project, how we can use in our real real ways.
Sandeep, my name is B. Abhinash. My friends explained introduction and execution of this project. Now I am telling about advantages, disadvantages, future enhancement, and conclusion of this project. Now I am telling about advantages of the project of IPC using shared memory. Advantages: it provides very high speed communication since we no need for operating system transfer data from two processors. Mm, it is very efficient, especially for the large scale large scale amount of data. Uh, there is also flexibility for developers, which they use tools like Semaphores or Mutex for safe access, and it also useful for low CPU power, ideally used in real-time operating system. Mhm. Now, disadvantages of the shared memory in QNX. Uh, we need very careful about synchronization because two processes try to write at the same time, so it may lead to errors. So we need to careful about that. And there are also disadvantages of security risky for the same memory, mm, and the developer must manually al- allocate and release memories, which adds complexity for this shared memory. Now talking about future enhancement, implement multiple process mhm, support, add priority based messages. We can expect new tools that automatically manage shared memory regions, and better debugging support can also help developers. Uh, these are the future enhancement. Uh, Now, conclusion of this project: inter-process communication system using shared memory in QNX Neutrino real-time operating system is one of the fastest and most efficient way for process to communicate. It, it plays key role in real-time and high performance systems, although it needs careful synchronization and security handling. But shared memory IPC will become even more reliable, secure, and developer friendly. This is about the project of interprocess communication system using shared memory. These are the references for, for this project. Thank you.